Alright, so let's say given this diagram here of a mass attached to a spring, and the question wants you to find the elastic potential of the block at a point x2 equals 5 centimeters. To solve, we can start by identifying in this system, energy is being stored in an ideal spring. So to keep this spring stretched by a distance of x, we must apply a force equal to kx, where k is the spring constant and x is the displacement. Derive the elastic potential energy from this force equation. First, find the work done to move the object from point x1 to x2, and we get this equation here, where this defines the work done on a spring. To get the elastic potential energy, we need to find the work the spring does on the mass between x1 and x2. If we look at this diagram here, Fs, which is the spring force, is going to be pointing in the left direction, and the force applied is pointing in the right direction, stretching the spring back. The spring will be doing work opposite to the work done by the force applied. Since if we remember, work is equal to force times displacement, and the displacement's in the right direction. The main consequence of this is that the work done by the spring is going to be equal to negative of the work done by the force applied, which is equal to the work done on the spring. It's going to be equal to this equation here. So if we look at the equation we just solved for the work done on the spring, it's just the negative of that. With this equation for the work done by the spring, we could define the elastic potential energy as this, where k is the spring constant, x is the displacement. If x is greater than 0, this is the case when the spring is stretched. If we draw out this diagram here, x1 equals 0, and then the spring is stretched at a position x2 equals 5 centimeters. X is going to be equal to x2 minus x1. This is the displacement, equal to 5 minus 0. So it's 5, it's positive. The condition where x is less than 0, this is going to be when it's compressed. So if we look at our diagram here, x1 is equal to 0, but x2 is going to be equal to negative 5 centimeters. Since it's compressed, it's on the left-hand side of the equilibrium position, x equals 0. And so if we do x2 minus x1, we get a negative. We can apply this to our example. By our elastic potential energy equation, x is going to be equal to x2 minus x1. x2 is going to be equal to 5 centimeters, and then x1 is equal to 0 centimeters. 5 minus 0 is just equal to 5, and then the k constant is equal to 5 newtons per meter. Note, we can't plug this in just yet. We have to convert the x into meters for the units to make sense here. So we can plug these two values in, and then we can compute the square on the right term. If we do that, we get this, and then we can compute the amplitudes in the units, and we get this for the final answer. So this is the elastic potential energy stored in the spring. Look at our diagram here. At the start position, the elastic potential energy is going to be equal to 0 because the spring's at rest. But when we stretch the spring out, it gains a potential energy. And this makes sense because when the spring is brought away from equilibrium, the force the spring applies on the object increases. Thus, there's an increase in the potential energy in the spring, which is converted into kinetic energy once we let the mass go. The mass is going to start moving back towards the equilibrium position.